Hello everyone, in this video I will present to you my implementation of the weak-heap data type in Isabelle. The weak-heap data type is an important stone for the implementation of weak-heap sort, which is an almost optimal algorithm for achieving minimal number of comparisons, which does not necessarily mean minimal number of recursive function calls, but rather the minimal number of per element comparisons. This is especially important for expensive comparisons like the full UTF Unicode comparison of strings. So what are weak heaps? Weak heaps are defined as follows. They have a root, which is the minimal element of the whole tree, and the left subtree of the root is empty, and for the right subtree of the root it has to hold that every node has two children except for the nodes on the very last layer and the nodes above. So only the last layer can be not fully filled. Note that while here it's depicted that the last layer is filled from left to right, actually the last layer may be filled sporadically, so there might be nodes here as well. Further, it has to hold that each root is the minimum of all the elements in its right subtree. So here you can see that 3 is actually smaller or equal than every element here, and 7 is smaller or equal 9. However, 7 is not smaller or equal 5, but this is okay because we have only a smaller or equal relationship to the right subtree. This, of course, also holds for the right subtree itself, so this is a weak heap. However, this is not compared with this node. Now, naturally, this definition was introduced on arrays, and most of the implementations work on arrays only. However, there are some functional implementations which have been put together for this proof of a working weak heap sorting mechanism. For implementing this data type in a functional form, we have to somehow keep track of this notion of layers, and this is done by introducing another value, a natural number that is passed into the invariant function, which notes how many layers this tree is meant to have, and a leaf may only be found on the 0th layer or on the second to last layer. So we introduced the original notion of the weak heaps and also split this notion into one which I call the almost complete notion, which is the structural invariant, and the so-called right heap notion, which implements the invariant of the element-wise comparisons. Of course, we also show that these notions are equivalent. Then this is only regarding the nodes of the tree, so we introduced a full weak heap as a node, as a tree, as a normal alien order tree, which left subtree is a leaf, which holds the minimal element of the whole tree, and further also holds a weak heap node which has as many layers as the tree is high. This is of course equivalent to the notion that the whole tree is a right heap, and only the right part fulfills the structural invariant. So one of the first statements in the papers about weak heaps is always a statement about the height and size relation, precisely that the height is the logarithm of the size plus 1, which we proceed to show as follows. First, we actually show that in comparison to a complete tree of the same height, we have at most half the size of the tree, which is to say that actually in the worst case, so to say, only the last layer may be missing from the whole tree. We show in another theorem that such a complete tree actually always exists, and from that we can deduce that the size is actually some power of the elements in the tree or its height, using the size of complete trees theorems. So using this and a slightly tighter bound for trees that are almost complete with respect to their own height, we can show the direct proof of the statement that the height of a tree is the logarithm of the size of the tree plus 1, upper bounded for almost complete trees with respect to their own height, which yields that for a full weak heap we have this same value plus 1 in the end. Note that here we remove the plus 1 because we require that the right side of the tree is almost complete with respect to its own height. So next off, we show some practical properties, especially a recursive property of the weak heap, which is also often stated in the paper, is that a weak heap that of some values, actually, if we consider only the right subtree, and choose the root as the new root of a weak heap, ignore the left sibling, but only take the right sibling, we get a new weak heap. This is easily shown by using a lemma that the weak heap node property is actually recursive with respect to its children. During the implementation of this, I noticed that actually every almost complete tree is balanced, so we can also show the theorem about its height in a more simple way, indirectly about the fact that it is balanced and already proven facts about the height of balanced trees. Further, we can actually show that every balanced tree is also almost complete with respect to its own height. So these notions are equivalent, and using the theory about Brown trees from the archive of formal proofs, where Brown trees are actually just balanced trees that are constructed from a list. So most naturally it's just the natural way of turning an array into a tree. We can use the same functions that create a tree from a list from this theory and deduce that these trees are almost complete with respect to their own height. So having already available such a tree that fulfills the structural inequality, we want to make sure that this tree also fulfills the heap property, or our right heap property, which is slightly weaker. So for this we implement the join function and sift down functions, from which we can derive a construction function which turns, as we show later, any almost complete tree in a tree that fulfills the right heap property, and also preserves all the multisets of the original tree. So for this we actually want to show that the number of comparisons is linear in the size of the whole tree, but this proof is actually omitted here. For sorting, we further need a function to delete any node, where I decided to delete the rightmost leaf because it most naturally is equivalent to deleting the rightmost node from a tree that is represented as an array, and based on this build a function that deletes the minimal element by removing the rightmost leaf and then sifting down the element. Note that it is not actually trivial that the rightmost leaf is always found and exists, because this has to be on the last two layers. However, we can show that for almost complete trees this function always returns something, and the tree where we deleted some element, it does always shrink regardless of the structural properties of the tree. From this, we can then implement a sorting function which is shown here. This takes a tree represented as a pair of its root and the right subtree and always removes the root, which is the minimal element of the whole tree, and then applies we keep sort on the tree that is obtained by deleting the minimal element of the right subtree. We actually have to show that this terminates because not trivially the size of this tree is smaller than is actually smaller than the size of the original tree. However, we have shown this before, and from this easily follows that this function terminates. So with some additions and the function that we have introduced before to turn a list into a weak heap, we can actually show finally that we have implemented a function that preserves the M set of a list but returns a list that is sorted with respect to the function smaller or equal.
Hello everyone, today I'll present my idea for the function data structures course, and my idea is on the Collatz conjecture. So first of all, what is a Collatz conjecture, or as it's also called the 3x plus 1 problem? The Collatz conjecture simply states that given this piecewise function, if we apply this function on a value of n repeatedly, so we apply the value and we take the output and we keep doing that, we will eventually converge at 1. Now what this function, this piecewise function says is the following, that if n is even, you divide it by 2, if n is odd, you multiply it by 3 plus 1. And what this part does is basically change, outputs an even value. So you can rewrite this function in this form, which is quicker, it saves you an iteration, by having this in the odd part, this division by 2. This is also called the sped up version of the Collatz function. All right, now let's look at the code. So what I did here in the code is the following. I have the Collatz function and the Collatz evaluate function. So the Collatz function basically does the iteration, and the Collatz evaluate function actually computes the value for a single iteration. And you can see that this is quite similar to the piecewise function, but the sped up piecewise function, but this is like more of a one-liner version of it. It basically uses the mod2n function, which an auxiliary function that basically does n mod 2, and it just checks if n is odd, then it will compute, this will evaluate to 3 plus 1 over 2, which is matching to what we saw, and if it's even, this will evaluate to basically 3 power 0 times n, so n plus 0 over 2, so n over 2. And the iteration here goes as follows. When you have iterated k times already, you just give out the same input to you. And if you end up with 1, you just give back the 1, because 1 is like the base case, and we can easily see that if you give the class function 1, after a few iterations you will get back to 1. And this is just for convenience, although the Collatz function is not defined as 0. I think this was added to make the proof simpler for induction. And finally, here is a non-trivial case which evaluates the function on n once, and then repeat the process k times. So what I show in this in my submission are two things. First of all, I show that I show a new approach on proving the Collatz conjecture, which references this paper, A New Approach Improvement by Wyron. So what this paper tries to do is provide a strong induction approach to prove the Collatz conjecture. So what it states is the following. For all k greater than 1, then for all n that are less than or equals k, if we can show that Collatz k that the Collatz conjecture holds for all these n that are less than or equals k, then we can show that the Collatz conjecture holds for all for k plus 1. So for one more than these guys. Now proving the base case for this statement is trivial, and I omitted it because you can just choose a small value of k and go about your proof. And it would make my proofs complicated. So what I try to prove here is just prove this statement that if you have the induction hypothesis, which is the Collatz conjecture holding for all n less than or equals k, I can show that the induction step holds for k plus 1. So for k plus 1. The thing is, you cannot just go with any value of k. You have to know what this value of k was, because if you try to simplify this statement, you need to know which part of the Collatz function you will go. Is it the odd part or the even part? So what the paper did is that it did the proof of this part of this implication for when k is odd and when k is even, and of the form 4 times t for all t greater than 1, so for multiples of 4, and also for even values that are of the form 4t plus 2, so basically the rest of the even values. So the paper was able to prove it for these two cases, so when k is odd and when k is even is a multiple of 4, and it was not able to prove it for that, and this was a challenging part, but still being able to prove it for these two values of k makes the problem simpler, because now you only need to prove the statement for when k equals 4t plus 2. And you can see that I proved it here for the odd values, I used this auxiliary lemma, and then I proved it for even values where the k is of a form 4 times t. And the basic idea of the proofs is that you try to simplify this induction step until you reach something relevant to this, and then you already know that this converges to 1. So for example, you try to find the k prime that allows you to reach this eventually. All right. The second part that I showed in my submission was a reduction of the Collatz conjecture problem. So basically, first of all, I need to introduce some terminologies quickly. So there's this idea of stopping time of n, which is basically the minimum number of iterations required for the Collatz conjecture, for the Collatz function, to give a value less than the initial input value. So if you provided 15, for example, how many iterations do you need for the output to be less than 15? And the total stopping time, which is basically the number of iterations you need to satisfy the Collatz conjecture, the minimum number of iterations. Now the proof states that if you can show that this for all n greater than or equals 2, because when n equals 1, that's trivial. For all n greater than or equals 2, if the stopping time of n is bounded, so in other words, that it exists, then for the total stopping time also is bounded or exists. And this idea of bounded just adds more complications, so I replaced this with something that gives the same meaning, which is that if there exists k, so if there exists number of iterations that gives less an output less than the input, then this is equivalent to saying that the Collatz conjecture holds for this value of n. And if this is true for all n, and if this is true for all n equals 2, then this is also true. And this is what I try to prove, that this equivalence holds. So to satisfy this equivalence, I first showed one direction. So from stopping time to total stopping time, and from total stopping time to stopping time. And using these two lemmas, I was able to prove this equivalence. And this result is a very interesting result, because now you can just, instead of trying to show that the Collatz function converges to 1 to satisfy to prove the Collatz conjecture, you can just show that the Collatz conjecture, the Collatz function starts sort of decreasing from the initial starting point. And these were just the two ideas I did in my submission, and I hope you enjoyed watching this video. Thank you.
Okay, so I want to give you a quick overview of my project. My project was about sparse matrices and vectors, and just a short introduction. What are sparse matrices? Those are matrices which contain mostly 0 entries, and thus it is more efficient for calculations and to store the matrix only by storing the non-zero elements. And the data type I chose for storing the elements is just as a list. So my representation is a list of pairs. The second entry is the element, and the first entry is the index of that element. And for vectors, it's the same, but just with one index and not an index pair. And there are some problems that arise with this definition, because not every object of that type will be a valid matrix. So let's look at some examples. So our first example is this one. This is a matrix which has an entry of 2 at position 0, 1 and an entry of 5 at position 2, 3. And this is fine, but let's look at the next example. What we have here is there are 2 entries at position 0, 1. One of them is 2 and one of them is 3, and this is not okay, because a matrix cannot contain 2 entries at the same position. And another thing we don't want to have is in this third example, namely we have an entry which is 0, because the idea of sparse matrices is to only store the non-zero elements, so we don't want to have this as well. So invariant function, which we call validity function, will map such a list to true or false, and it will map it to true only if no 2 elements are at the same position and no 0 is contained. And this you can see here in this definition, which is recursively defined. So first of all, the empty list is always valid, and then if we have a list containing more than 1 element, then the head element must not be 0, and in the tail there cannot be any other element at the same position, and of course the tail has to be a valid matrix as well, and the same goes for vectors. So let's look back at our examples which we already had, and we see that our first example is fine, but our second example is not valid. Why? Because there are 2 entries at the same index, and our third example isn't valid as well, because there is a 0 that is contained. And in order to show that this validity function is exactly what we had in mind when defining it, we will show a lemma later on, but first of all we will define some more functions we can use to extract entries of matrices. So those are those functions, and what we see is that we have some auxiliary functions going on, which, given for example a matrix and an index, extracts all entries which are at that position. And of course we only want that 0 or 1 elements are at one position, but this is just an auxiliary function which makes some lemmas a little bit more easy. And then we can say, okay, if we are interested in the entry at that position, we just return the first of that list, or 0 if the list is empty. Remember that in sparse matrices, elements that are not explicitly stored are assumed to be 0. And some other functions which are going on here are get row and get column of a matrix. matrix. Those are pretty self-explanatory and are just defined over filters. And now here are some lemmas which show in some sense that those functions we defined are correct. So for example, I think the most important one is this one and this one. So if we have a valid matrix, then the get method returns 0 if and only if ij element is not contained in the matrix, and if we have some non-zero element, then the matrix returns that element at that position if and only if that element is in the matrix at that position. So now with all this work, we can show that the validity function is what we had in mind when defining it. So a matrix is valid if and only if for all index pairs it holds that there's at most one entry in the matrix and there is no zero element in the matrix. And the proof of this is quite a bit work. So the first direction, if we look into the proof, if we assume to have a valid matrix, it's rather easy because I defined some lemmas which state exactly those things, and then it follows rather easily this right hand side. But the other case requires some work, although we have some auxiliary definitions. So it is, it assumes this right hand side and shows the left hand side by induction on M, and the easy case is the nil case, and the more complicated one is the cons case. And we use some lemmas here, and despite that it is quite some work. But finally we get this nice characterization which actually shows that our validity function is what we had in mind. Next of all, we will show some simple conversions from vectors to matrices, because we can interpret vectors as matrices, and how well this depends on whether we want to interpret the vector as row or column vector. So in the first case, if we want to interpret this as a column vector, then we just say, okay, the ith entry of the vector is actually the i0th entry in a matrix, and in the other case it's the other way around. And then we can show some easy lemmas which are just saying that if we get an element of that vector at position I, we can as well get it off the corresponding matrix at the i0th position or 0ith position. Now an easy matrix function which one often considers is the transpose function, and this is rather simple because if we want to transpose a matrix, then we just reverse each index pair, so map ij to ji and leave the elements as they are. And what follows quite simply is that the transpose function is idempotent. That is, that if we apply it twice, then it is the identity function, which can easily be shown by induction. And the next thing is that this function is as well correct. This is also pretty easy because it follows for our auxiliary function just by induction, rather simply, and then it even follows for the get entry function even if we don't have a valid matrix, but especially it follows if we have a valid matrix. And moreover, this function preserves validity, so the transpose of a matrix is valid if and only if the matrix is valid, and this also is rather simple proof. And now some other nice lemmas are if we had those conversions from vectors to matrices, so if you interpret vectors as matrices, and now we can show that actually if we interpret a vector as row matrix and then transpose it, it is the same as just interpreting it as a column vector and vice versa. This also follows pretty simple. And moreover, if we remember our get column and get row functions, then those can be transformed into each other as well with the transpose function. So the kth column of the transpose matrix is just the kth row of the original matrix and vice versa. So now let's look what we can do with a transpose function. So first of all, what we can show if we look back is that a vector is valid if and only if it is valid if interpreted as column vector in a matrix, and moreover we have that a matrix is valid if and only if all its rows are valid vectors. And with the transpose function we now get the same results if we replace here column by row or here row by column, and this is rather simple. We just apply transpose and the propositions we just had, those lemmas here, and get the corresponding result. Again, this proof is just 6 lines long. And now let's skip over some other things I showed in my theory. So first of all, we had so far no method of updating the entries of a matrix, and now we define such a method which just sets at some index the matrix to some element. And what is important is that this function preserve validity. So if we have a valid matrix, it is also valid after the update. Next of all, we will define a function to delete rows and columns of a matrix, which will become useful for later on when we define the matrix multiplication. And we show again that if we have a valid matrix, then after deletion, the matrix is still valid. And now finally, let's get to some interesting stuff, that is algebraic operations, such as addition. So we now require our elements to be ring elements, and then we can define the addition, but we have to ensure if one matrix contains an element and the other matrix contains the inverse of that element with respect to the addition, then we cannot store this element because we have a sparse matrix. And now we will show two important things about this addition. First of all, it preserves validity, and second of all, it is correct. That is, if we get an element at some position, it is just the sum of if we would have gotten that element at those two matrices. Next of all, we show that this addition is associative, and for that I actually have to admit I did it rather complicated, because you can look at this. I have two auxiliary lemmas. One is this and the second one is this. Those are quite long, and then I start to prove the actual associativity lemma, rather complicated by induction. And what I could actually have done, but only noticed after I submitted, is that I can just use the correctness proposition to get the associativity, which looks like this. So as you can see, this is much simpler. And next of all, let's look at the runtime. And the runtime is actually not that good for the addition, because the way I defined it is we have for each element of the first list we have to go through the second list, and so the runtime basically is bounded by the product of the lengths of the two lists. The exact bound is given in this proposition, and as you can see, it is quadratic in the lengths of the input. And this runtime could be improved if I had not chosen some list as representation, but some kind of balanced tree, as we saw in the lecture. Now let's move on to the scalar multiplication. This is rather simple. We just multiply every element with a scalar we want to multiply the matrix with, but we have to be careful, because we are in the setting of a general ring, and especially this ring can have divisors of 0. So even if this S is not equal to 0 and this element is not equal to 0, the product can be, and so we have to catch that case in order to preserve our validity. And a small enhancement we can do is, if S is equal to 0, so we want to multiply a matrix with 0, then we just immediately return the empty list. Now the next algebraic operation is the scalar product of two vectors, but this is rather simply defined just with an auxiliary function. So let's just move on to the matrix multiplication. Now let's look at the matrix multiplication, which I implemented quite complicated. The reason for this is that I wanted to exploit in some way. I know that my data type is not the most efficient one, but I wanted to at least exploit the sparse structure and not have a horrible runtime. And so I only considered entries that actually appear in the matrices. And the problem is now that I had not in my invariant function some kind of sortedness constraint, and so this function is rather nasty, because the rows could be scattered along the list as well as the columns. And so what I had to do is, first of all, define an auxiliary function and then define the actual multiplication function. And how I did this is, if the first matrix is the 0 matrix, the product is again the 0 matrix, and otherwise I look at the first entry which is there, and then I just take the complete row in which this entry is and multiply it with each column of the second matrix. And this is what this multiplication auxiliary function does. And after that I delete the row, because I already multiplied it with the second matrix, and multiply all other rows with the second matrix. And now let's look at the auxiliary function. This is similar. Again, if the second matrix is the 0 matrix, the result is just the 0 matrix, but otherwise we look at the first element and then extract the column in which this element lies. Here is actually a mistake. This should be column. And now what we do is we multiply those two vectors with the scalar product, and now we have to check if it is 0 to preserve validity, and if it is not 0, then we append the corresponding entries to the product matrix. So this multiplication method is rather complicated, and I even had to define an auxiliary function to prove termination. I added it to the sim set, so it is not explicitly here, but it is required to show termination.